Hello everyone. Today we shall start with the module number 3, bipolar junction transistor. So bipolar junction transistor, in short it is called as BJT. So you are aware of the BJT or bipolar junction transistor. You have studied this in first year. The basic of this one is it's a transistor with three terminals, that is emitter, base and collector. It consists of two junctions, that is PN and NP. So here a bipolar junction transistor is basically a very simple device with a three terminals, namely called as emitter, base and collector. So we begin this chapter with a discussion of charge transport, that is carriers, electrons and holes transport in a bipolar junction transistor to establish a physical understanding of the operation. So in this chapter we mostly use the PNP transistor for most of the illustrations. The advantage of this one is for discussing the PNP transistor is that whole flow and current are in the same direction. So this makes the various mechanism of carrier transport or charge transport somewhat easier to visualize in a explanation. So once if you get the basic ideas for established for the PNP device, it is very simple to relate them more widely used transistor, that is nothing but the NPN transistor. So first let us discuss the fundamentals of BJT operation. So this figure shows a PNP transistor. A PNP transistor is a three terminal device. It consists of three terminals, that is emitter, base and collector. So the figure shows the schematic representation of a PNP device with a forward biased emitter junction and a reverse biased collector junction, that is figure number 1 or figure A. So forward bias is nothing but the emitter and the base. Emitter is P, that one is connected to the positive of the battery, and base N, which is connected to the negative of the battery. So the first PN junction make that transistor forward biased, and the next junction NP junction. So N is base is connected to the positive of the battery, and negative of the battery is connected to the P, that is collector. So this junction NP junction makes it reverse biased. That's why a forward biased emitter junction and a reverse biased collector junction. The second figure shows the VI characteristics or voltage current characteristics of a reverse biased NP junction, that is the second junction NP junction, the reverse biased NP junction as a function of emitter current. So these are the figures that are displayed here. So let's discuss what it is, fundamentals of BJT operation. So we know the diode function, that is diode works in a forward biased and when it works in a reverse bias. So similar to that one. So here we are considering the PNP transistor, a convenient hole injection device, that is a forward biased P plus N. Observe there the emitter is P plus, that is it is heavily doped, plus stands for P plus N junction. So here the current in such junction is due to the holes that are injected from the P plus region into the N material. If we make the N side of the forward bias junction same as that of N side of the reverse bias junction, then the P plus NP, that is whatever that is shown in the figure, that will be the result. So with this configuration, the injection of holes from the P plus N junction, that is the forward bias junction, into the center N region supplies the minority carriers, that is holes, to participate in the reverse current through the NP junction. Of course, here you need to know that the injected holes do not recombine in the region before they can diffuse to the depletion layer of the reverse biased junction. Therefore, we must make the N region narrow compared with the hole diffusion length. Observe there, all the three regions, N region, P region and P plus region, the N region is narrow as compared to the other hole diffusion length. N region, observe here in the figure, it is very narrow as compared to the other two. So the structure that we have described here is a PNP BJT transistor, PNP bipolar junction transistor. So the forward bias junction that injects holes into the center N region is called the emitter junction. So whatever the forward bias junction that we are talking about, that is going to inject the holes, it will forcibly, it injects the holes into the center N region, the base region, which is a N region. It is at the center, is nothing but it's a emitter junction, and the reverse bias junction that collects the injected holes. So whatever that we are injecting the holes from the emitter junction, that will be collected, that holes are going to be collected, is called as what? The collector junction. It is in the reverse bias junction that collects the injected holes, which is nothing but a reverse biased junction. Here the P plus region, which serves as the source of the injected holes, as we are injecting the holes from this side, it is nothing but a source, it is called as the emitter. So emitter is a source of holes, and the P region into which the holes are going to be swept by the reverse bias junction is called as the collector. So why the name is collector? Because it collects the holes which is injected from the emitter. So the biasing arrangement is called as common base configuration. So this kind of configuration is called as what? Common base configuration. Why it is called as common base? The name common base is because we have three different combinations, configurations: common base, common emitter and common collector. And this configuration is called as common base configuration because the base electrode, whatever the center one, the N region, the base electrode is common. So that base electrode is common between the emitter and the collector circuit, that is left side as well as right side. There are emitter and collector terminals are there. In between there is a base. So this base is common between the emitter as well as the collector circuit. That's why this is called as common base configuration. To understand a good PNP transistor, we would prefer that almost all the holes that are injected by the emitter into the base will be collected. So therefore the N type base region should be narrow. As you can see from the figure, N region of the base, that is very narrow, and the whole lifetime tau p should be long. The whole lifetime, which is denoted as tau p, should be very long. So this requirement is summarized by specifying WB. So that is shown in the figure. WB is much less than LP. So where WB is the length of the neutral N material of the base and LP is the diffusion length for holes. LP is the diffusion length for the holes in the base. dP tau p raised to half, or square root of dP tau p. So with this requirement satisfied, suppose if this this requirement is satisfied, an average hole injected at the emitter junction will diffuse to the depletion region of the collector junction without recombination in the base. There is one more requirement here, that is second requirement is that current IE crossing the emitter junction should be composed almost entirely the holes injected into the base rather than electrons crossing from base to emitter. So this requirement is satisfied by doping the base region lightly compared to the emitter, so that P plus N emitter junction results. So as you can see here, P plus stands for heavily doped region, N just N, it is a lightly doped region. So this is the result. The second figure, this shows the summary of hole and electron flow in a PNP transistor with proper biasing. So whatever previously we have seen, the same figure that is continued here, but it shows the summary of a electron and hole flow in a PNP transistor with a proper biasing. So it is clear that IE, that is emitter current, flows into the emitter of a properly biased PNP transistor, and the IC, that is collector current, that flows out of the collector. So observe here in the figure, the IE is flowing into the emitter, whereas the collector current IC is flowing out of the collector. IE is flowing into the emitter and collector current IC flowing out of the collector. Since the direction of the flow of the current flow from emitter to collector here, therefore, but the base current IB requires some more thought here to understand. So in a good transistor, the base current will be very small, it is very negligible, since IE is essentially a hole current and collected hole current IC is almost equal to IE. We know that IC is approximately equal to IE. That's why the IB is very negligible, that is base current is very negligible. There must be some base current, but here there must be some base current due to the requirement of a electron flow into the N-type base region. So we account for IB physically by three dominant mechanisms. There must be, first one is there must be some recombination of injected holes with electrons in the base, even with WB is much less than LP. The electrons lost to recombination must be resupplied through the base contact. The second one, some electrons will be injected from N to P in the forward biased emitter junction, even if emitter is heavily doped compared with the base. So these electrons must also be supplied by IB, that is base current. And the third one is, some electrons are swept into the base at the reverse biased collector junction due to thermal generation in the collector. So this small current reduces the base current IB by supplying electrons to the base. In the figure, you can observe there are numbers 1, 2, 3, 4 and 5. That one shows the injected holes lost to recombination in the base. So it is shown in the middle one, that is in the base N region, that is one shows the arrow mark that is going upward. It shows injected holes lost to recombination in the base. Number 2, that is shown in the collector region, P region, it indicates that hole reaching the reversed biased collector junction. The holes that are shown from the emitter, it reaches the collector. That is the indication. Number 2. 3. The two arrow marks are shown, that is hole and electron in the P region of the collector. So it shows thermally generated electrons and holes. Electrons and holes both are shown here. Thermally generated electrons and holes that are making up the reverse saturation current of the collector junction. That is number 3. Number 4. that is shown in the middle. Again, it is in the base region. So it shows that electrons supplied by the base contact for recombination with holes. So the arrow mark that is coming downward from the in the base region. So it shows that electrons supplied by the base contact for recombination with holes. And the last one, 5, that is shown in the emitter region, number 5, that is in the P plus region. It indicates that electrons injected across the forward biased emitter junction. That arrow mark, cross arrow mark shown from the base towards the emitter, it indicates that electrons are injected across the forward biased emitter junction. So here the dominant sources of the base current are two. That is, first one is the recombination in the base, and the second one is the injection into the emitter region. So both of these effects can be greatly reduced by the device design. So in a well designed transistor, IB will be very small fraction of IE. So remember here, IB is very small, it is very negligible as compared with the current IE. That is, base current is very negligible compared with the emitter current. So in an NPN transistor, the three current directions are reversed here. So in a PNP, we have discussed about the PNP transistor. In a NPN transistor, what happens is all the three current directions are reversed: emitter current, base current, and collector current. All the three directions are reversed, since electron flow from emitter to collector, and holes must be supplied to the base. The physical mechanisms for operation of NPN can be understood simply by reversing the roles of electrons and holes in the PNP, whatever we have discussed. Thank you for watching the video.